This video is on the objective write a Cartesian equation in polar form. And this is the second video on this. I'm hoping you watched the first one where I went over a little more. So I'm just going to get right into the problem. All right, so again, if you want to see more on the topic, click on more instruction, look at their videos, their notes, their examples, and hopefully those help you. Alright, so here we're given an equation in rectangular coordinates, Cartesian coordinates, right, x's and y's. And we're asked to, translate it, convert it to another equation in polar coordinates with r's and thetas, such that the graphs of both are exactly the same. Right, the graph of this equation in rectangular is exactly the same curve as the graph of, one of these equations in polar. Alright, so let me take this to a piece of paper. Alright, so the equation we're given here in rectangular coordinates in x's and y's is this: x squared minus y squared equals 2x plus 3y. Now again, I'm hoping you remember all the relationships between polar and rectangular coordinates, right? I wrote these up last video. Remember, x squared plus y squared, so I'm seeing minus y squared there. I can't use this right now. X squared plus y squared will be equal to r squared. X equals r cosine theta, y equals r sine theta, and the tangent of theta is y divided by x. Okay, so let's keep these in mind and try to use them. But before I do that, let's see, what would the graph of this look like, in the rectangular coordinate plane, the Cartesian plane? Well, hopefully this looks familiar to you. You might say, oh, this is a hyperbola. Remember from like pre-calculus 1 or from a previous algebra class you may have taken. Right, if I take x squared and then minus 2x, then leave a little space here, minus y squared minus 3y, and then have that equal 0. Then I can complete the square here. This is x squared minus 2x, and then I would add 1 to complete the square. Add 1 over here. Here I can't complete the square because the lead coefficient is not positive 1. I factor out minus 1. And then I'd have y squared plus 3y, and then I complete the square in here, and this would be adding 9/4. Now if I add 9/4 in this set of parentheses, what I really did was subtract 9/4 from this left side, so I got to add 9/4. I'm sorry, subtract 9/4. Because if I really subtracted 9/4 from the left, so I got to subtract 9/4 from the right. Alright, and then we have this. We have the quantity x squared, or x minus 1 squared, minus the quantity y plus 3/2 squared, equals, and then this is 1 minus 9/4. Be negative 5/4. Okay. Alright, and then I would divide everything by negative 5/4, and this would give me, the positive, you have y plus 3/2 squared divided by 5/4. And I'm writing it this way for a reason. And then minus the x minus 1 squared divided by 5/4 equals 1. Right? And this is in that general formula, the general version, the general equation for a hyperbola. Right, a hyperbola. And the graph of this thing, and I'll bring it up on that desmos.com website. But the center of this would be 1 for x, negative 1.5 for y. Right, there's the center of the hyperbola. And you'd go up and down, like the vertices, the transverse axis would be vertical here. And I'd go up and down whatever the square root of 5/4 is. Right, so there's something here, and I'm going to have a hyperbola. All right, I'm just going to draw some rough hyperbola, all right, something like that. And let me show you. Right, let me actually show you the graph of this on in a better drawing on a website. All right, so I'm going to this desmos.com. It's a free online graphing calculator. And I'm just going to type in the equation the way it started. It was x squared minus y squared equals 2x plus 3y. Right, you see the hyperbola? And the center, right? The center is at the point. The point actually halfway between them is at, I said it was 1 comma and then negative 1.5, right? And you can see that red point that just came up is exactly halfway between these two curves, these two branches of the hyperbola. All right, so got that up, right? This curve. Now the question is, what's the polar equation that has this same graph? So again, I'm using all those relationships I showed you, and we're going to go through, and I'm going to cover this for now. We're going to go through and change our equation in rectangular with x's and y's so that it's in r's and thetas. So remember, everywhere I see x, I can replace it with r cosine theta. So instead of x squared, I got r times cosine theta squared. Right, there's x squared. Minus, and then y squared. Well, instead of y squared, that's r times the sine of theta squared. And the same thing on the other side. This would be 2 times r cosine theta, right, instead of x, plus 3 times r sine theta instead of y. All right, then squaring all this, I'd have r squared, and both of these would have r squared in it. So what I'm going to do is factor r squared out. And then we have cosine squared theta minus sine squared theta. And then this is equal to, again over here, 2 times r cosine theta plus 3 times r sine theta. All right, now one solution to this would be r equals 0. But r equals 0 is an uninteresting graph. R equals 0 is just the origin. That's the only point where r is 0. So one curve that's coming out of this is r equals 0, but that's uninteresting, right? That is not the graph we're looking for. We're looking for this graph, this hyperbola. So I'm going to get rid of r equals 0 here and just divide through by r. Notice that both sides have a common factor of r. Right? Both terms over here have an r. This is a factor of r. So I'm going to divide out that common factor of r, divide by r, and we have r times, now this might look familiar to you, I'm hoping, cosine squared theta minus sine squared theta. A much simpler way to write this, right, just because I don't feel like writing all that again, is the cosine of 2 theta. Remember the double angle formulas. Remember the cosine of 2 theta was equivalent to cosine squared theta minus sine squared theta. And it equals this, right? But without the r's, I'm dividing through by r. So 2 cosine theta plus 3 sine theta. And then typically we're going to have to solve for r. Right? If I look at all my choices here, go back to the problem. Seeing all these choices, they have r equals, r equals, r equals, and then the other side is in terms of theta. So let's do that on my paper. Solve for r. Just divide by cosine 2 theta here. So r equals, in the numerator, 2 cosine theta plus 3 sine theta. And then all of that divided by the cosine of 2 theta. And this is actually one of our options. And the graph of this equation in polar, if you were plotting points on a polar grid with the circles, would plot all these points here. It would look exactly the same as the graph of this hyperbola in the xy equation. And let me show you that. All right, let me go back to the Desmos website. Okay, so here is our graph in rectangular coordinates. Now if you type with x's and y's in Desmos, it graphs you in rectangular. If you type with r's and thetas, it graphs you in polar, which is really nice about this website. So if I graph r equals, and then in the numerator, 2 times the cosine of, now for the letter theta, you can just type in the word theta, and it changes it to theta, plus 3 times the sine of theta, T-H-E-T-A. Then all this divided by the cosine of 2 theta. And look at that. And I'll have theta. Now I know theta ranges from 0 to pi. Usually we want theta to range from 0 to 2 pi. So I'll set that up. And look at this. Let me turn this off for a second. Right here was the graph, the black graph in rectangular coordinates. See, when I changed it to polar coordinates, when it's graphed in polar coordinates, it's right on top of it. It's the exact same curve. All right, I'll turn this one off, and you can see it's still there, that hyperbola. So that's it. Right? That is what we want to select. R equals 2 cosine theta plus 3 sine theta, all divided by the cosine of 2 theta. Would be the same, have the same curve, the same graph, but on the polar grid, right, instead of in rectangular coordinates. But would plot the exact same points, the exact same locations. Wonderful. All right, again, they kind of show you just what I did a second ago. Right. All right, and again, this can be tricky. All right, these first 2 videos, I'm only doing these 2. You might see some other types of equations. I would say, from rectangular, from Cartesian to polar is kind of simple. Just replace all the x's with r cosine theta, all the y's with r sine theta, and then you might have to use some identities, like how I did cosine squared minus sine squared was the cosine of 2 theta here. You might have some identities come into play, but I feel like it's easier to go from rectangular to polar equations than it is to go from polar to rectangular, as you'll see in some other videos. But just remember those relationships, right? Those 4 relationships that I wrote up, these here, one more time. If you remember these, it should make the transition a little easier to deal with. Okay? All right, so hopefully watching me do this, looking at more instruction when you need to, reading the answer explanations when they come up, right? I'm hoping all this stuff helps you out when you're working on this material on your own. Okay, thank you very much for watching.